Hey everybody, I want to explain the two-sample F-test, which is sort of our precursor to ANOVA, which I will explain a little bit later. ANOVA is the kind of thing that we're really going for with the F statistic. But first, let's learn about a two-sample F-test, which is a very simple version, sort of. It's not really ANOVA at all. Anyway, let's go back to the notes. So here's what a two-sample F-test is. I'm going to assume you watched the last video. A two-sample F-test compares two variances, right? If you remember, what an F statistic is it's a ratio of two sample variances. And so what we're going to do with a two sample F test is test to see if it's reasonable to think that two variances or that two population variances are equal if we have two sample variances, right? So we're going to have a sample from one population, we're going to test this variance, or we're going to find its variance, and we'll take a sample from another population, we're going to test its, or we're going to find its variance, then we'll make a ratio out of them. And that ratio is an F statistic, and then we will use an F distribution to determine if we think that S1 and S2 are far enough apart that it makes us think that sigma 1 and sigma 2 are different from each other. That's what a two-sample F test does. It tests to see whether the two population variances are plausibly equal or not. That's what you're doing there. So I'm going to pause this recording for just a second. I want to go get something open, and then I'll be right back. All right. So the thing I wanted to get open was my old notes from chapter 10, where you may recall that we had a test that we did called a two-sample t-test, right? I presume you remember the two-sample t-test. And in it, there was an option. Let's go here. So if I go to stats, tests, and two-sample t-test, this guy right here, there was a pooled option. And at the time, I told you, just leave it on no. We don't really have the expertise to talk about what it means to be yes. What this is asking you is, are these two samples, do these two samples plausibly come from populations with equal standard deviations or equal variances, I should say? And in order for you to find that out, you have to do a two-sample F test, which is the thing we're going to learn about right now. So that's why I couldn't really tell you about how you determined this yet at the time, right? 3 weeks ago or whatever, 2 weeks ago, because we didn't have the necessary test. Now, the gain you get from, or the gain in sensitivity that you get from using pooled standard deviation is pretty marginal. It's really not even worth thinking about. So we're not gonna go back and rediscuss this. Just keep using no. If you would like to, I will have an extra credit question on at least the final, but I think I have one on test 3 as well. And if not, I guess I can put one on there that asks you to determine if you should use pooled or unpooled for some hypothesis test that I give you. And you have to identify that the way you determine pooled or unpooled is by using a two-sample F test. So let's talk about that two-sample F test. So what a two-sample F test does, as I mentioned a minute ago, is it determines whether two populations, whether it's plausible to believe that two populations have the same standard deviation or not. So you can do that in 3 different ways. It's the same 3 as always, right? The null hypothesis is everything's equal. And the alternative hypothesis is one of them's bigger or smaller than the other one, or they're just not equal to each other. There is a two-sample F test function in your calculator, at least in the calculators that I know of in the TI 84s or 83s and 84s. But honestly, it's so easy to do by hand, you barely even need it. So let's see it. Let's see what this looks like. Now, again, when we're talking about standard deviations and variances, the English word that we end up using is consistency a lot of the time. So let's look at this example. So I want to see if a newer machine is more precise in making nails of the right size than an older one. right? I've got this old machine in my nail factory, which I don't know why I have a nail factory, but I do. And I'm thinking about buying this new machine, and so I want to see if it gives me any benefit, right? Does it make better nails? And better, as far as this is concerned, is probably means more consistently sized, right? That's the real test here. Is, are my nails all the same size, or do I get all these wonky weird ones with a high variance? So I would like to keep the standard deviation, or the variance of the nails, to a minimum. So old machine gives us a sample of 48 nails with a standard deviation of 0.38 inches, 0.038 inches, and the new machine gives us a sample of 53 nails with a standard deviation of 0.026 inches. Now, a couple things. Thing number one, you can increase the precision of your f-tests by doing the same sample size. So these are close, so that's good. They could be the same. I just wanted to make them different to emphasize the different degrees of freedom. Like if you use the same number everywhere in a problem, it becomes hard to differentiate between what's going where. And so I wanted to make them different so you could see where they were different. But in general, if you have an f-test to do, make your sample sizes the same. It will make it slightly more precise. So I have this sample, 48 nails, 0.038 inch standard deviation, 53 nails, 0.026 inch standard deviation. And I want to know, at a significance level of 5%, can I say that the new machine makes more consistently sized nails than the old machine? So let's get a whiteboard going here. So here's what I've got. I've got new. We get n equals 53. We had not sigma, excuse me, s. S equals 0.026 old machine. We had n equals 47. Did I say 47 or 48? I don't remember. 48. S equals 0.038. So let's make these let's put some subscripts on these. I want to not just call these n and s, right? I want them to be n's and s's, of course, because that's what we use for sample standard deviation and sample size. But computer, come on, there we go. But I want this to be n sub new and n sub old and s sub new and s sub old. Right. So I'm going to use subscripts to identify what my standard deviation and sample size are. So the sample size is where I'm going to get my degrees of freedom from, right? My degrees of freedom on the new machine is going to be 52, and the degrees of freedom on the old machine is going to be 48 or 47. This is actually not the number I want. This is S. This is the sample standard deviation, but I want the sample variance. Remember that F equals S1 squared over S2 squared. So here I'm going to have, I'm going to call the new machine 1 and the old machine 2. So we're going to have n squared over SO squared. And so within that, we're just going to go calculate that number. Excuse me, my computer's telling me one of my videos is done encoding. That's fantastic. All right, so here's what we're going to do. I'm going to switch over to the calculator. We're going to get out of here. And I need to find my, I put new on top, so new is 1. So we're going to have S n squared. So we're going to have 0.026 squared divided by 0.038 squared. Right? So that is my F statistic. F is 0.468. That's it. So you find an F statistic. You just take variance squared, or just take variance of one over the variance of the other. So let's put that here. So we're going to have equals 0.468. That's my F statistic. Now my degrees of freedom for the top is 52. So this is, let's make a new page. So we get something that looks kind of like this. This is F52, comma 47, right? So my numerator degrees of freedom go first, and my denominator degrees of freedom go second. And I had so mean of 1, and I had a 0.468, which is over here. 68. That was my F statistic from this test. And so I need to write some hypotheses, right? This is a hypothesis test. I need to get some hypotheses going. So the question was, does the new machine make nails that are more consistently sized? Does the new machine make more consistently sized nails than the old machine? That is to say, does the new machine have a lower standard deviation or lower variance than the old machine does? So in other words, is sigma sub n less than sigma sub O? Right, so if 1 is n and 2 is O, then I am doing this guy. Right, is my variance of the new machine less than the variance of the old one? So let's go write some hypotheses. So I've got my null hypothesis H naught sigma sub n squared is equal to sigma sub O squared. And my alternative hypothesis is that sigma sub n squared is less than sigma sub O squared. Now, let me just caution you to be quite careful about the order you do things in. I always want to write this in thing I put on top, thing I put on the bottom, right? On top, on the bottom. And if you do that, then this will point you in the direction that you want to shade, right? So less than means that I want to shade to the left. If you mess that up, you might have to shade the other direction. So be really careful that you're keeping the order straight, right? It goes top, then bottom, top over bottom, top over bottom, right? And the reason you want to put it in that particular order is that, well, one mnemonic device you can use is same thing here, top, bottom, right? So area I am looking for is over here. This is my p-value. This is, excuse me, the probability that if it is the case that the null hypothesis is true, where they have the same population variance, so these two machines have the same population variance, then this area over here is where I would see an F statistic as extreme as the one that I got, which is 0.468, or that is more extreme. More extreme meaning more in the direction of the new machine having a lower standard deviation than the old one, or lower variance than the old one. So this area right here is the area I want to look for, which is, of course, FCDF. I'm going to do FCDF from 0 up to 0.468 with 52 and 47 degrees of freedom, and that's my p-value. So let's flip over to the calculator. And we will do distributions, FCDF from 0 up to 0.468 with 52 and 47 degrees of freedom. Paste it all in. We get a p-value of 0.004. So you can tell my picture is not very well to scale, right? So really small, really, really small, which is smaller than 5%. That's 0.4%, so much smaller. So my p-value equals FCDF 0 to 0.468 with 52 and 47 degrees of freedom. It's about equal to 0.004, which is less than 5%, which I don't know if I specified a alpha or not. I should probably go look. Did we specify one? 5%, look at that. I picked the standard one, great. That makes us want to reject our null hypothesis, right? So we've got So we got reject a null hypothesis. So that makes us think that it is not the case that the two machines have equal standard deviations, but instead we think this is the case, that the new machine has a smaller variance than the old machine, which is good. That means it is more consistent. So this data suggests that the new machine makes more consistently sized nails than the old one. There you go. That's how you do a two-sample F-test. Now, let's go look at the kind of the easy way in the calculator. There's just a button for it, right? It's a test. So if we go if we go to stat and tests, there should be a two-sample F-test here somewhere. Yeah, there it is, two-sample F. So we have summary statistics, not raw data. So one was the new machine, correct? So we're going to do, we said that was 0.026. N1 was 53. This was 0.038, and with a sample size of 48. And we were testing to see if sigma 1, the new machine, is smaller than the standard deviation for the old machine. Notice that when they're doing a two-sample F-test, they're stating everything in terms of standard deviations, which is totally fine. I've been using them interchangeably here, and they're not technically the same thing, but they kind of serve the same purpose. And so this really is what you're testing, right? If one variance is smaller, the standard deviation is also smaller. So this is a fine formulation of a way to put it. It's just that the F statistic actually does technically use variances. So I've been saying variance. So let's calculate it up. Hey, look at that. It's exactly the same thing we got before. So not much to say there. I do want to kind of draw it just to see what it looks like. Tests. Oh, yeah, two-sample F. We're going to do the same exact thing, but I'm going to draw instead of calculate this time. Oh, pardon me. I still have an old graph on there. This is what I get when I. Oh man, Turkey! I hate that it deletes it when you do that. Example F. Draw, please. There we go. So you can see that my picture was a little bit off, right? It's a little bit flatter at the beginning than I drew. Well, it's a lot flatter at the beginning than I drew it. And you can see there's this tiny, tiny little area here. And so that's why our p-value is so small. And as before, like here's 1, right? So that's where the mean is, pretty much where the peak is. So 0.468 is way over here. And there you go. That's it. That's a two-sample F-test. There's not much to it. Feel free to go ahead and use it in your calculator to just type it into the two-sample F-test in the calculator. But again, if your calculator doesn't have this, it's barely any harder to just calculate the F statistic yourself and then use FCDF. It's really like not a big deal. Yeah, and I think that's all I want to say about the two-sample F-test. So what the two-sample F-test is for is it checks to see if two population variances are equal or not. Equal, like you can also do greater than or less than. When you're doing a two-sample F-test, make sure that you are putting the one on top first in your hypotheses, because that will cause your alternative hypothesis to have the sign pointing in the direction that you want to tell you which way to shade for your FCDF. Otherwise, it can get a little confusing. But yeah, so top then bottom for everything. Degrees of freedom in your hypotheses. It's not technically wrong if you do it the other way around. It's just you can easily confuse yourself and get tricked. And with that, I think I want to just stop here. So let me go ahead and wrap up here. So in the next video, I'm going to explain ANOVA, which is a particular kind of two-sample f-test that's really clever. And the cleverness makes it a little bit complicated to understand. So I'll explain all that in the next video, and then I'll show you how to. Now, the actual doing of ANOVA for our purposes is simple. Like there's really not much to it. ANOVA is really sensitive to assumptions though. So there's a bit more to it, but there's an ANOVA button in your calculator. We're just going to use it. Like that's how we're going to find all of our p-values and whatnot. So don't sweat the math. The math actually gets really nasty, kind of, and we're not going to do any of it by hand. We're just gonna put in the data and hit the ANOVA button and see what we get. But because ANOVA is so sensitive to assumptions, we're going to check assumptions, and we're going to be pretty rigorous about checking assumptions. And that's where actually the trickiness will come in. So, all right, we'll go over all of that in the next video, and then and then that'll be it for ANOVA. All right, so I will see you guys in the next one.